Okay, thanks for the introduction. And Mengjie WU from Shanghai Astronomical Observatory, and I will today talk about the GNSS radio occultation data applications in the ionospheric data assimilation and scintillation studies. I will send to my co-authors, one of my colleagues, and the other one is the CEO of the company, Kalman, who provides the majority of data maybe referred in this study. So this is the outline. I will just skip it and begin with the background. We know that the accomplishment of GNSS systems and the low Earth orbiting satellite missions will provide us increasing number of high quality of data, and those data are now widely used in the numerical weather prediction and reanalysis field, as well as some space physics and space weather researchers. Since we know that the GNSS receiver, the RO receiver on board the LEO satellite will receive the signals passing through the whole ionosphere and atmosphere, so we can use some methods to retrieve the essential parameters from these signals and to get the interesting information we need in the ionosphere, like the electron density. So on the right side, the picture shows the daily coverage of a cosmic tube, which consists of 6 RO satellites. And we know that it's a great advantage of the RO data to have a relatively average global distribution. So recently, there were 2 satellites that have being launched into space. One is called the TGU-01, which was launched by the company Yunyao, and it was equipped with the RO receiver in 2021. And the other one is called the MSS satellites, which is one of the satellite project missions in China too, and it was launched much recently. And maybe also you already heard about some other RO missions in China, like Kalman, and so on. So both the scientific and commercial groups are exploring the possibility of RO platform with lower cost and energy budget, and to explore their applications in ionosphere and atmosphere researchers. But before we use those RO data, we should make sure that the RO data has a comparable or reasonable quality with other data resources like the GNSS results. So on the left side, the top panel showed the several satellite missions we are already familiar about, like the JSON, the Sentinel, the Cosmic, and of course, for the ground-based stations received by the IGS observations. Before comparing directly the RO data and the IGS like gene products, we should keep in mind that the RO mainly focuses on the ionosphere and its base altitude. So there is a big gap between these 2 data sets. So here we use the POD observations to retrieve the ionospheric electron content above the LEO satellites. And with those 2 VTCs combination, we will make a comparison with the IGS gene final products. And for the results, we have done that for 2 years, 2008 and 2014. And the results show that the RO data has really small bias between with respect to the gene products, but we see that a little bit hemispheric symmetry exists in the gene, but generally they agree well with each other, with the STD varying from 1.5 to about 6. And so we will use the cosmic tube and the ionosound also as the reference to validate the TGU-01 and the MS-1 satellite RO data. So here are showing some results like with comparison with the ionosound. Sorry, I'm too short. The results with the ionosound and cosmic tube, and we see the we compare the HMF2 and MF2, the critical parameters in ionosphere, so they have the comparable accuracy, and also these are results for the MS-1. So in this point, we can see that our data just hides the comparable accuracy with other radio occultation observations of the ground-based the ionosounds. Besides the ionospheric modeling or monitoring thing, we also are interested about how the ionosphere is changing in much short term. So we will focus on the scintillation or the irregularity which causes these scintillations. So in the cosmic tube, there are already high rate signal-to-noise ratio records transmitting to the ground, and also it carries IBM inside the equipment to explore the scintillation and the irregularity directly from the satellite. And for TGU and MS-1, they also provide the high rate signal carriers or the phase data to do the such researchers. Here gives an example of how we can use those phase or amplitude data to direct the scintillation. So here in the carrier noise time series, we can see at about 100 km/h there existing big fluctuations. So this is the highly possibility to be an ES or cyberotic E occurrence. And with the power spectrum density analysis method, we can retrieve some essential parameters about the irregularity which induce this scintillation. And we see the finally in the electron density profile, we can see there is also a bump at the E layer. So in this way, we can locate the scintillation in the RO signals. Here we use 3 months MSS-1 RO data to make the global map of ES and equatorial plasma bubbles occurrence rates shown at the left picture. So for the ES occurrence, we can see there is obvious predominant semidiurnal patterns and separated by the epoch or sunrise. But for the EPB, their occurrence are much focused after the local sunset till the early morning, but they are rarely found during the daytime. And also we look spatially in the South Atlantic anomaly region, which has extremely low geomagnetic magnitude. So in this picture. So the color map shows the electron density peak height in actual layer, and the black dot shows the occurrence of ES or EPB. So we see in the EPB's map, there is a high coherence between the electron density enhancement and the occurrence of these scintillations. But for the ES, the relationship is not formed. Well, the last part, the data assimilation. Since we outhype the space-borne technique and the ground-based stations, so the data assimilation is regarded as a good way to combine different observations from different techniques. So here we propose a strategy called step-by-step data assimilation, which means we will divide the whole atmosphere into two parts, the lower grade and the higher grade. The higher grade means we will separate the ionosphere above the Leo altitudes. So we will use the periodic observations to do the data assimilation, firstly at the higher grade, and when we update the background, then we will go continue to the lower grade and do the similar thing. So in this way, we get the data assimilation model of the electron density, which could be 3D or three-dimensional or 4D, and also the temporal variations of the NMF2 or HMF2, which are very essential in the ionosphere. So for the validation, we use several ionosonde stations located in different latitudes. And for here, you can see the orange line shows the original background models like II or NIPIC, and the blue line shows the observations from the ionosonde. And after the data assimilation, you can see the NMF2 will get much closer to the ionosonde, which we think is more accurate. And also, the data assimilation results will well reproduce the detailed structures in the ionosphere, but the background seems so smooth. And also the step-by-step data assimilation strategy will give us a much better background reference before we do the data assimilation in the lower ionosphere. And in general, we will get a better coherence between the assimilated model and the ionosonde model, like the STD below 20%, I think. And so I will stop at the conclusion, and thank you all for your attention.